This extension is done in two stages. First, I'll take the f, which is integrable, and I'll take g, which is integrable and essentially bounded at the same time. So in fact, although I call it extension, currently the way it looks, it's even more restrictive than the case we discuss here. Yet it will be an extension in the proper sense, and listen to this. First, I will do a sort of informal manipulations of the same nature. Look at this. If I compute the integral of the convolution with respect to my Lebesgue measure, now I sub in the what we have as a definition of a convolution. It's a proper definition because g is an essentially bounded function, f is summable. For that couple of functions we do have a proper definition. Here it is. Now what I'm going to do, I'm going to use the comparison principle, and I'm going to take the absolute value to the integrand here. Here it is. Now I'm going to replace this repeated integral with the integral over the product measure space. That's the product measure space. That's the product measure. It's a function of two variables, x and y. And now I'm going to put the repeated integral in the other order, where now the x integration becomes the inner integration and the y integration becomes the outer integration. Now, all of these manipulations, they are done in modern research papers. These kind of manipulations are very often, and the mechanics behind these manipulations, it is a Fubini's theorem. Normally people don't comment on that, but once, like I promised, I'll give you the details of this, of the way Fubini's theorem works here. In fact, when you try to formally justify these identities or justify this argument, you have to move the other way around. You have to move this way. First, you have to look at this repeated integral, and I claim now that when I look at this repeated integral, if I call this bracket a function h, like this, if this bracket is a function of variable y, in fact, and if I give the name for this function h, then I claim that this h function, here it is, it has the following structure. Because it's an x integration, this is just a constant which comes out here, and inside we have a translation of the function f by the number y. Now, because of the transfer of measure theorem or substitution, this is just a number which is identically equal to this thing, and your function h ends up to be just a scaled function g, scaled by this number. We know that the function g is integrable. It's here in my assumption, so my h function is also integrable. Yes, my h function is also integrable. Now, by Fubini's theorem, I can now claim that because of this function is integrable, I can now claim that the function on the product measure space is also integrable. And now, by applying the Fubini theorem again, I can claim that a repeated integral in the other order produces the function here in the bracket, which is also integrable. But the function in the bracket, that's my convolution function like this. So the step, in fact, this chain of identities and inequalities, in fact, shows you that the integrability of the function like this implies the integrability of the function like this, and that is the way Fubini's theorem works. Again, in the modern analysis papers, people often just skip this detailed explanation how the Fubini works, and I find it's reasonable, but for the people who try to see the inner mechanics of this kind of arguments, I made this demonstration just to give you this explanation how the Fubini works once. Now we can conclude my estimate, because now I can say that the left-hand side here, which is the L1 normal of the convolution function, is controlled by the right-hand side here, which is integral of my h function, and that's a constant times the integral of g, and you end up with the inequality like this. This one is also called Young's inequality. It's another special case of Young's inequality. Okay, now, like I mentioned earlier, although I call it extension, so far it looks like it's even more restrictive than the one we had earlier. But for the experienced analyst, in fact, all I just did here tells everything he needs or she needs to know. Because if you look at the inequality we just established, you can realize that although g is required here to be bounded function, nowhere in this inequality we have a dependence on the how bound this function is. Nowhere in this inequality we have a dependence on the infinity norm of the function g. And that actually allows to do a proper extension via the Cauchy sequences and the fact that this collection of functions is Banach space. Listen to this. That's the second step of my extension. If I now have function f which is integrable and the function g which is also merely integrable, no longer will require any bounded conditions, look what I'm going to do. We all know that we can find a sequence of functions which is integrable and bounded at the same time, which approaches to my g in L1 norm. Now, if I introduce my Hn functions, which are the convolutions of f with Gn, these are the properly defined functions, because g is a bounded function. We all know that these Hns will be summable. That's my first part of my extension. Yeah, this is the limit when n goes to the infinity. Moreover, if I look at the difference like this, this will change into the expression like this. You can just put the difference in one of the components of your convolution. Now, observe that f is integral function here, and this bracket, this is summable and bounded function. So I can use this step in my extension, in my first step of my extension, and estimate this value by the expression like this. And now this is a sequence which converts to g. So this is a Cauchy sequence. So we have this goes to 0 if m and n goes to infinity independently. And what we see, we have a sequence of Hns from L1 class, which is a Cauchy sequence. By the fact that this is a Banach space, there must be a limiting point. There must be a limiting point, and it is very natural to call this limiting point the convolution of the function f in g. That's how the convolution is defined, where g and f are L1 functions alone. And that's my convolution. Again, this symbol no longer makes any sense in the proper Lebesgue integration sense, but it does make sense according to this argument. And of course, we still have the Young inequality for this extended version of the convolution. I emphasize this again, that although people write this expression for the convolution in this very general context, it only works because of this argument, and in fact this integral in a proper sense doesn't make any, in the proper way doesn't make any sense.